Let's see here. All right, so let's talk about acids and bases. So, this unit is going to have a couple videos kind of broken up. In the PowerPoint videos, we're going to talk about basically what's in the book. We're going to look at some theory, and then I'm going to do a couple videos with math problems that go with acid-base equilibria. So, if you're looking for a math problem, we'll go over a couple here, but we're not going to really work any in depth until a different video. So, start here and get through the PowerPoint notes, and then we can move on to the examples. So let's jump in. The Arrhenius definition of an acid basically says that if you put a substance into water and the concentration of hydrogen ions increases, then it's an Arrhenius acid. If you put a substance in water and the concentration of hydroxide ions increases, then it's a base. So Arrhenius looks at the concentration of hydroxide or the concentration of hydrogen, all right, ions, just like that. Now, Arrhenius definitions are limited. They are restricted to aqueous interactions, all right? So Arrhenius, think aqueous. The second definition, and I know we learned these last year, but just going over them, is the Brønsted-Lowry definition of an acid. It is not limited to aqueous environments. And it says that an acid is something that donates a proton, and a base is something that accepts a proton. And again, when we're talking about a proton, all right, we're talking about H plus, okay? Now, looking closer at the Brønsted-Lowry definition, then in order to be a Brønsted-Lowry acid, you have to have at least one removable proton, and we call that proton the acidic proton. So here, in the example of hydrochloric acid, there's only one, right, acidic proton. There's only one proton, so it has to be the acidic proton, and it can be removed, all right? When we remove it, we're going to donate it. All right, and the way we do that is we take these two little lone pairs and we draw a little arrow right there and we say, hey, I'm stealing this, and then this bond, those two electrons go live on chlorine, and so I'm left with a chlorine species with a negative charge on the right, and this interesting looking molecule, H₂O+, H₃O+, which is hydronium. All right, and we're going to want to know that word, hydronium. Now, if you're going to be a Brønsted-Lowry acid, you have to give up a proton. If you're going to be a Brønsted-Lowry base, you have to have at least one set of lone pair electrons in order to steal that acidic proton, in order to accept that proton. So in water's case, water in this reaction is acting as a Brønsted-Lowry base. All right, let me move that down just a little bit. There we go. And here I have a Brønsted-Lowry acid. Now, this is also, in this case, all right, acting as an Arrhenius acid because it is producing hydrogen ion increase in solution. Right? And we'll get more into this in a minute, but something to keep in mind, we use these two things pretty much interchangeably when we are discussing acid behavior. All right. Now, something that is interesting about this hydronium ion, it's worth noting, is that hydronium ions can still form hydrogen bonds because they have that lone pair. And so, you know, hydronium can be attracted to the hydrogens on another hydronium. All right, there's my lone pair. And there's my hydrogen bond. And this can lead to some really interesting things. It can lead to clusters of what we call hydrated water, which gives you stuff in solution like H₄O₂+, which is, you know, interesting, right? One of those interesting things. So what makes water different? Why can water be an acid and water be a base? Well, it's pretty simple. Water can donate a proton because it has two of them, right? So let's just say that one. There's my acidic proton. So it can donate that proton, which can make it acidic, or it can accept a proton, and that's going to make it basic. All right. So the word that we use to describe this is amphoteric, okay, which means it can act as both an acid or a base. Now, when we look at an acid-base reaction, we do want to obviously be able to identify the acid and the base, but we also want to be able to identify the conjugate acid and the conjugate base that are left on the product side. So the term conjugate means joined together as a pair. So the acid and the conjugate base are a pair, and so we could say acid conjugate base and the base conjugate acid. All right, those are the two pairs, BCA, ACB. Okay, and when I want to identify them, I just look for who has lost an acid, an acidic proton, who has lost their ability to be an acid. Sorry. So I've definitely got an acid over here on the left. It starts with my H, and this is HNO2. And in this case, water is acting as a base because it's going from H2 to H3. So H2 to H3 means I have to add, right, an H plus. And so this over here is now my new conjugate acid, and the thing that made it is the base. On the other hand, I have HNO2, right, and it's becoming NO2 minus. So I had to subtract an H plus. So this must be the acid, and that must be the conjugate base. And hopefully you remember doing this in first year chemistry. Now, honestly, right, everybody loves to talk about how strong acids are. That's one of the things that I encounter with a lot of my first year chemistry students. Like, oh yeah, acids really cool. And acids are really cool. I'm not in any way, putting that down. But it is important to be able to talk about the relative strength of acids and bases. So we want to know the difference in a strong acid and a weak acid, right? A strong base and a weak base. And I guess fortunately enough, there is kind of this reciprocal relationship between acids and bases. So the stronger the acid is, in this case, let's look at HCl, the weaker its conjugate base is going to be, right? So remember, acid conjugate base, right? So if I have HCl plus H2O, I'm going to get Cl minus, and I'm going to get H3O plus. So HCl, very, very strong acid, right? It's one of the three strong binary acids. But the conjugate base that it makes right here is extremely weak. It has negligible basicity in solution, okay? Now, on the other hand, if you go down here to the bottom and you look at something like CH4, right, we look at methane. Well, methane is not a very strong acid, okay? But if we were to get it to do this, right, let's put it in water, and let's get CH3 minus and our H3O plus. Now, this conjugate base is very, very strong because this is such a weak acid. So the weaker the acid, the stronger the conjugate base. Okay. Now, if you are below the line where water is acting as an acid, so right here, then you are a strong base. All right. And their conjugate acids will not act as acids in water. They have negligible acidity. So like O2 minus, right? If we were to put O2 minus into water and we were to get OH out, well, OH minus is not going to act as a base there. Okay. So when we look at when we look at the relative strength of an acid or a base, just remember, the stronger the acid, the weaker the conjugate base, or the stronger the base, the weaker the conjugate acid is going to be. Now, whenever you have an acid-base reaction, equilibrium, which is something we've discussed quite at length now in AP Chem, is going to favor the transfer of the proton from the stronger acid to the stronger base to make the weaker acid and the weaker base. So when I look at this reaction that we've now looked at on a couple different slides, and you go, all right, well, why does it make H3O plus and Cl minus? Why doesn't it make, say H2Cl and OH minus, right? Well, water is a stronger base than Cl minus. Let's go back and confirm that, right? So as we go down this chart, we get stronger bases. we see that water is stronger than Cl minus. So since water is a stronger base than Cl minus, the equilibrium, the K value, is going to be greater than 1. It's going to lie far to the right, okay? And in that case, we're going to see a reaction that proceeds to the right. We're going to make products. Now, if we take a weak acid, like acetic acid, which we have here, this is acetic acid. Remember from your first year chemistry naming rules for acids that if you have acetate as your polyatomic ion, 8 becomes ic. So acetate as an acid, and there's the acidic proton. They write it on the end so that you see it by itself. Acetate becomes acetic acid. Now, acetic acid and water is at equilibrium with H₂O plus, so hydronium, and our acetate ion. Now, in this case, our acetate is actually a stronger base than water. So let's go find it, right? We just look on the tape. So there's a stronger base than water is. So our K value is going to be less than 1, and our equilibrium is actually going to favor the left side. So, think about vinegar, right? Vinegar is like 97% water, and we'll say 3% CH₃COOH. Now, when I put acetic acid into water, I don't have to worry about it completely ionizing. It's not a strong acid in this case. And so it remains relatively to the left, right? I have acetic acid molecules, I have water molecules. Now, there are some H₃O plus ions floating around in vinegar, and if you drink straight vinegar, it will taste sour because it is acidic, all right? But the equilibrium itself is going to shift, in this case, to the left. And again, the only way I'm establishing that, or the easiest way I'm establishing that, not the only way, is that I know that acetate is a stronger base than water. So it's really important that you get familiar with this table, okay? So just kind of look over it, reference it often, okay? Use it. This is something we want to use, this table right here. You could even write it down in your notes for easy reference. So let's move on. Let's talk about water a little bit. Water is interesting as an amphoteric molecule because it can auto-ionize. So what that means is that water can attack itself, right? Remember that auto from biology. Auto means self. So it can self-ionize. So when water is in pure water, so a solution of pure water, singular water molecules will attack other water molecules, and they will produce hydroxide, and they will produce hydronium. Now, because we have this situation, we can express that using, the equilibrium expressions that we've already learned. So we can say that K, in this case Kc, is equal to hydronium concentration times hydroxide concentration. Now, this is a really special equilibrium constant, okay? It's called the ion product constant. It's got a name, right? There it is, ion constant product for water, and we abbreviate it Kw. Now, Kw is 1 times 10 to the negative 14th. And you've probably seen the number 14 when we discuss pH, right, and acids and bases. So this Kw is going to be coming back in a minute. But before we get there, remember that when we look at an aqueous solution, we either classify it as acidic, basic, or neutral. If you're neutral, we know that the concentration of hydrogen ions or hydronium ions, remember they're interchangeable, is equal to the concentration of hydroxide. If it's acidic, we know our concentration of hydronium ions is greater. If we have a basic solution, we know the concentration of hydronium ions is less than the concentration of hydroxide ions. And you'll notice that I have referred to each of these based on the behavior of hydronium or hydrogen ions as it relates to OH. Because when you look at pH, pH is telling you about the H plus concentration. Now, if you look at POH, we would then refer to it in terms of hydroxide, all right? But that's just a little, language clue as far as to whether or not we're talking about pH or POH. Now, the pH scale is something you're probably familiar with. make sure you know this equation right here. pH equals the negative log of the concentration of hydrogen, or, pH also equals, right, the negative log of the concentration of H3O plus. It is very, very important that you understand that H plus and H3O plus are completely interchangeable, because sometimes they'll give you one and sometimes they'll give you the other. All right, we use them interchangeably when we talk about acids and bases. Now, as you probably remember from last year, the neutral pH is 7. Probably known that since middle school. We know that acids have pHs below 7. We know that bases have pHs above 7. Now, you can look here and see the concentration of hydrogen as given by molarity. Okay, so for really strong acids, right, you might have a concentration of 1 molar, right? In a 1 molar solution of acid, you're not going to have much in the way of base, right? Like 1 times 10 to the negative 14th. But their concentrations, okay, have to add up to 14 right there. When you multiply, not add up, sorry, sum up to 14. So, wow, not sum up. They must form the product of 1 times 10 to the negative 14th when you multiply the concentration of hydrogen times the concentration of hydroxide ions. So, 1 times 10 to the 0 times 1 times 10 to the negative 14th. In this case, right, when you multiply exponents, you add. So I get 1 times 10 to the negative 14th. And that's what I have to get. So that is a really, 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 really useful piece of information. If you know the concentrations and you multiply them, you will get 1 times 10 to the negative 14th. If you have the pH and the pOH and you sum them, you will get 14. So there are 3 really important formulas on here. There's number 1, there's number 2, and there's number 3. So jot those down. You're going to be using them. Now, there are other P scales, right? The P, it stands for power. All right, the power in pH tells us to take the negative log of the quantity. In this case, for pH, we're doing hydrogen ions. If it's pOH, then we're doing hydroxide ions, right? You could also do the pKw, which would be the negative log of Kw. So anytime you see that P out front, it means take the negative log of whatever that thing is. So if I had, let's just make one up. Let's say P fancy star. Well, that would be equal to the negative log of fancy star, right? That's what P means when you see it. Now we can put pOH and pH together, like I just said a minute ago. We know that the multiplication of the concentration of hydrogen ions and hydroxide ions is going to give you 1 times 10 to the 14th. And remember, that's Kw, all right? We can take the negative log of that equation, and we can get 14. pH plus pOH equals pKw, or 14. Now, we'll talk more about log rules in one of the little math videos that I'm going to take, because obviously you don't get a calculator on the AP Chem test, so we want to be able to approximate some things with log rules. So look for that in one of the math videos that I'm going to make for this unit. Now, in the lab, we definitely measure pH a lot of different ways, okay? We can use indicators like litmus paper, or things like phenolphthalein, which change color in the presence of a base, or an acid, right, depending on what the indicator is. Phenolphthalein changes color in the presence of a base. If we want to make I thought I was going to yawn there. If we want to make a pH reading for quantitative values, a really accurate number, we use a pH meter. These are electrodes. They measure the changes in voltage in a solution, and they have a computer program inside that equates that to a pH. Now, there are 7 strong acids we want to know, okay? HCl, HBr, and HI you memorized in the first year of chemistry. Nitric acid, sulfuric acid, HClO3, and HClO4 are ones that we're going to add to that list of memorized strong acids for AP Chem. Now, something to remember when it comes to oxy acids, all right, if we want to determine if they are strong. If we do O, the number of O, right, number of oxygen, minus the number of H, and we get a number that is greater than or equal to 2, then it's strong, okay? So let's just make up an acid here. Let's say I have H₃X₂O₃, whatever, we just made it up. Well, 9 minus 3 gives me 6, so this made-up acid would be strong. But let's say I had, H₃X₃O. All right, well, 1 minus 3 is -2, so this would be a very weak acid. So remember that with oxy acids, we can always figure out if they're strong, but memorize these 7, right, with these 3 old ones and 4 new ones. Now, if you are a strong acid, by definition, you're a strong electrolyte, okay? And that means that when we put you into water, you completely dissociate. You'll see the yield arrow, all right? You use a yield arrow for strong, all right, because you have complete, okay, dissociation. Now, on the other hand, if you see a weak acid, so like let's say CH₃COOH plus H₂O, it's going to be at equilibrium. H₃O plus, and then our acetate ion. So if you see this, all right, think weak. If you see that, all right, if you see the straight arrow, think strong. All right. If you know you have a strong acid, then whatever the concentration of the hydronium ion is, it's equal to the concentration of the acid. So what do I mean by that? Well, let's say we get some word problem, and it's like, you're using, I don't even know, 1 times 10 to the -1 concentration of HNO3 in a problem. And I need to know the concentration of hydronium. Well, there it is. Because I know this is strong, right? This is a strong acid, then that concentration of the acid equals the concentration of H₃O plus, which is the same thing as H plus, right? Remember, these two things are interchangeable. So make sure you know your strong acids, and make sure you know if it's monoprotic strong acid, then there we go. The hydronium concentration is equal to the acid's concentration if it's given to you in the problem. Now for strong bases, we learned the strong bases last year, right? They haven't changed. We know that the soluble hydroxides, so our alkali metals, our group 1 metals, plus OH, and then the heavier alkaline earth metals, so calcium, strontium, barium hydroxides are strong. Beryllium and magnesium hydroxide are weak bases, all right? So if you think about, I need to find a periodic table. Hold that thought. Yeah, so like if we think about the group 2 of our periodic table, the first 2, beryllium and magnesium, are weak, but the rest of them, these 3, all right, as we go down, are strong. I would assume that one would be strong as well, all right, as we go down the list. But calcium, strontium, and barium are the most common ones we are going to use. I doubt I would use radium hydroxide for anything, since radium is radioactive, and, I'm not going to mess with that. Just like strong acids, if you have a strong base, then they are going to completely dissociate in solution, all right? So we get the yield arrow again. If we had a weak base, same thing, right? We would expect to see the equilibrium arrow instead. And when we have weak acids, right, it is at equilibrium. Anything at equilibrium has an equilibrium constant. And in this case, we call it the acid dissociation constant, all right? Now, we identify that as Ka, okay, right here. There it is. Where, Ka equals the concentration of hydronium times A minus, all right, which A minus is over here. So let's remember, we have acid conjugate base. We have base conjugate acid. So here's my acid. This is my conjugate base. So we have the concentration of our hydronium. I'm just going to rewrite this. Times the concentration of the conjugate base over the concentration. All right, what's HA? All right, well, that's our, or sorry, divided by, well, yeah, over. HA is our acid. Okay, gives us K sub A, the acid dissociation constant. The greater the Ka, the stronger the acid. All right, so that's something we definitely want to know, right? If you have a really large Ka, then we have a very strong acid. If we have a very low Ka, well, then we don't have a very strong acid. When we compare strong and weak acids, all right, the main thing that we're really talking about is just, do they completely dissociate or do they not? That is a qualitative description, all right? If I really wanted to, look at quantitative, I would have to use Ka, and we'll do that in the next slide. But as far as your just qualitative description, strong acids completely dissociate, weak acids just partly dissociate. So let's look at a problem when we calculate Ka. Now, I am going to do some other videos with math problems, but I'm going to run you through this one because this one is a pretty easy one. It's in the book, and I liked it, so I'm going to throw it into this first half of the Chapter 16 videos. So let's just look at calculating Ka from pH. So here's the problem. It says the pH of a 0.1 molar solution of formic acid, which is HC₂OH, at 25 Celsius is 2.38. So I have the pH. Calculate Ka for formic acid. All right, well, what do we know? We know that Ka is going to be equal to the hydronium concentration times our conjugate base concentration over our acid concentration. We need to have all three of those. Now, we can figure out the concentration of H₂O plus from pH. How can I do that? Well, I know that H₃O plus equals HCOO minus, those two concentrations. I know that that's going to be equal to 10 to the negative 2.38, because there's my pH, right, from our basic understanding of acids and bases last year. And so that gives me 4.2 times 10 to the third. Well, let's plug that into an ICE table, all right? This is the exact same table that we used earlier in the year to do equilibrium. We're still talking about equilibrium, and so now we can figure out our concentrations. So we know that our initial formic acid concentration is 0.1. It goes right here. It's our first thing. All right. We know that the ion concentrations at time equals 0 are going to be equal to 0, right? So there's 2. We have the equilibrium ion concentration, which we just calculated. So it's right here. Here's 3. All right. And that gives us both of those categories. And so now we can just figure out the change. So we do final minus initial, right? So here's final, here's initial. Final is after the change, right? So equilibrium is our change. So 4.2 times 10 to the negative third minus 0 is 4.2 times 10 to the negative third. That's going to be the same for both of these. And that means that the change over here is negative 4.2 times 10 to the third. So we're going to say, we're going to use this arrow. It means it follows. So logically speaking, if this one went up 4.2 times 10 to the negative third, this one must have gone down. So we do 0.10 minus 4.2 times 10 to the negative third gives me 0.0958, which for sig figs gives me 0.1 at equilibrium. So now I can put in all my numbers, and I find that Ka is 1.8 times 10 to the negative fourth. Oh, dropped my pen. Now, if you need to take a minute, go back and look at that, please do. I am going to work some more of these math problems in a different video, so we're just going to kind of keep moving. But that is the basic gist, all right? We're going to pull stuff out of the problem. We're going to plug it into an ICE table, right? Initial, change, equilibrium. And then we're going to take that information, right, from that data table to solve various questions, in this case, Ka. All right, we're almost done. We're going to do a couple more slides and to finish up the first half of Chapter 16. If you need a break, take a break. So let's look at something called percent ionization, all right? Percent ionization is the amount of is the amount of hydronium you have at equilibrium divided by the amount of acid you started with, both in concentrations, times 100. This is still going to be part over the whole times 100, right? It's the acid part, so the H plus part, over the HA. Oh, excuse me. Where HA is the whole acid there, the hydrogen and whatever non-metal it's hooked to. So if we go back to our formic acid, we say that we had 4.2 times 10 to the negative third, all right, divided by 0.1 times 100. We have 4.2%. Well, this is a weak acid, right? We know that weak acids typically, or weak electrolytes typically dissociate less than 5% in solution, and we certainly have a number that's less than 5% in solution. All right, let's look at going the other way. Let's calculate pH from Ka. So 4 steps to this. We're going to write the chemical equation for our ionization equilibrium. We're going to write the equilibrium constant expression, which hopefully you know, right? That's our formula. We're going to do an ice table. But just like we did in the equilibrium unit, now we're going to plug in an X value for some of those concentrations. And then we're going to use the quadratic formula to solve, right? So we're going to substitute our equilibrium concentrations in and solve for X. So we have calculate the pH of a 0.3 molar solution of acetic acid at 25C. All right, well, the first thing we need to do is write our expression, right? Write our equation. So we have acetic acid. There it is, acetic acid plus water is at equilibrium, right? What's the assumption here? Right? If we're able to do this, it must be weak. We're calculating that as an equilibrium to make our hydronium ion and our acetate ion. All right, we know that Ka is equal to H plus, all right, here we go. Ka is equal to H plus times our conjugate base over our acid. There it is. And so now we can plug things in. All right, well, what do we know? Well, we know that in the end, the change in H plus and the change in CH3COO minus is going to be X, it's going to be the same. So we know that their changes are just going to be plus X. We know that the initial concentration of our acetic acid is going to decrease by that same X, right? It follows, right? This is a logical conclusion. And thus, the equilibrium concentration will be 0.3 minus X for acetic acid. So let's plug that in. Well, I have X squared divided by 0.3 minus X. Well, if you're going to assume that X is much less than 0.3, then we have 0.3 minus X is going to be 0.3, okay? It's going to be very small. And we can assume that because we don't want to use the quadratic formula. So in this case, we're going to say that 1.8, let me move the face here, 1.8 times 10 to the fifth is going to equal X squared over 0.3. So X is going to be 2.3 times 10 to the negative third. Now that we know X, that's our concentration of hydronium. So if I want to find the pH, I take the negative log of that number, and in this case, I get 2.64. And we'll look at some more of those in the math videos. But these are good to have, good to run through. They're in the book, so we'll definitely chat about them. All right, last slide. If we're comparing strong and weak acids, just another way we can explain their comparison. We can look at the concentration of hydrogen ions at equilibrium compared to the acid concentration initially. If they're the same, it's strong. If, however, the initial concentration is greater than the equilibrium concentration, well, then we must have a weak acid. All right, so that's another way we can describe it. All right, so that's going to be the end of the first video. We'll do the second half of chapter 16 notes in the second video. All right, but if you have any questions, let me know. Okay, this would be a great slide for you to just jot down the formulas, okay, that we have covered so far. All right, and if there's any questions you have, jot them down too, send them to me, and I'll talk to you about it. All right.